What if there was a programming language that was simple, fast, and built for modern systems? That's Go, also known as Golang. It was designed to handle real-world problems like scalability, performance, and concurrency. Go is a strongly typed language. This means every variable has a defined type, and you can't mix them incorrectly. This type safety helps catch errors early, making your programs more reliable and easier to debug. Go is a compiled language, which means your code is turned into a machine-level program before it runs. This makes it much faster than interpreted languages that execute code line by line. You get both speed and efficiency right out of the box. One of Go's biggest advantages is its fast compilation speed. Even large projects compile quickly, improving developer productivity. And with built-in concurrency using Goroutines, Go makes it easy to run multiple tasks at the same time. Go is designed to be simple and easy to read. Its minimal syntax reduces complexity and helps developers focus on solving problems. That's why Go is widely used for backend systems, cloud infrastructure, and high-performance applications. Let's start by creating a new project folder for our Go code. This keeps everything organized and easy to manage. Open this folder in your code editor. And now we're ready to write our first program. Create a file called main.go. In Go, every program starts with a package declaration, so we write package main. Then we import the FMT package to print output. Finally, we define the main function, which is where our program begins. Inside the main function, we can now write our first line of code. Using fmt.println, we print a message to the console. This is your first working Go program. To run the program, open your terminal and type go run main.go. This command compiles and runs your code in one step, so you can instantly see the result. Inside the main function, we can now write our first line of code. Using fmt.println, we print a message to the console. This is your first working Go program. Variables are used to store data in a program. Think of them like containers that hold values such as numbers, text, or true and false. In Go, you can declare a variable using the var keyword, followed by its name and type. For example, var age int, or var name string. This makes your code clear and type safe. Go can also figure out the type automatically. When you assign a value, the language infers the type for you. This reduces extra code while keeping things safe. The most common way to declare variables in Go is using the short declaration syntax. Just use :equals, and Go will handle both declaration and type automatically. You can also declare multiple variables at once. This is useful when working with related data and keeps your code concise. Go has a few basic data types: integers for whole numbers, floats for decimals, strings for text, and booleans for true or false values. These are the building blocks of most programs. Go also provides different integer sizes like int 8, int 16, int 32, and int 64. These allow you to control how much memory your numbers use. Unsigned integers, or uint, can only store positive values. They're useful when you know your data will never be negative. Floating point types like float 32 and float 64 are used for decimal numbers. And in Go, every variable has a default value, called a zero value. Numbers start at 0, strings are empty, and booleans are false. Constants are values that never change. You define them using the const keyword. They make your code safer and more predictable. And now you understand how variables and basic types work in Go. Control flow decides how your program runs. It controls which code executes, when it runs, and how it repeats. This is what makes your program dynamic and intelligent. The if statement lets you run a code based on a condition. If the condition is true, the code inside runs. Otherwise, it is skipped. Go also allows a short statement inside the if condition. You can declare and use a variable in the same line, making your code more concise. You can extend conditions using else, if, and else. This allows your program to choose between multiple paths based on different conditions. Comparison operators are used inside conditions. They compare values and return true or false, which drives your program's decisions. Logical operators combine conditions, and requires both conditions to be true, while OR requires at least one to be true. The for loop is used to repeat code. In its classic form, it includes initialization, condition, and increment. This allows precise control over how many times the loop runs. Go doesn't have a separate while loop. Instead, you use the for loop with only a condition. You can also create an infinite loop, and stop it using break. The range keyword lets you loop over collections like arrays or slices. It gives you both the index and the value in each iteration. Switch statements provide a cleaner way to handle multiple conditions. You can match values directly or even use switch without an expression, making it behave like a flexible if-else chain. As programs grow, repeating the same code becomes messy and hard to manage. This is where functions come in. Functions let you group logic into reusable blocks, making your code cleaner, easier to read, and easier to maintain. In Go, functions are declared using the func keyword. You give the function a name and define what it should do inside the curly braces. Functions can take inputs, called parameters, and they can also return values. This allows you to pass data into a function, process it, and get a result back. One powerful feature of Go is that functions can return multiple values. For example, you can return both a result and an error at the same time. This makes error handling more explicit and easier to manage. Go also supports name return values. You can define the names of the return variables in the function signature. This can make your code more readable, especially in more complex functions. Sometimes you don't know how many inputs a function will receive. Variadic functions solve this by allowing a variable number of arguments. They're useful when working with lists of values. In Go, errors are treated as normal return values. Instead of exceptions, functions return an error alongside the result. This makes error handling explicit and forces you to deal with problems properly. In Go, functions are first-class citizens. This means you can assign them to variables, pass them as arguments, and even return them from other functions. You can also create anonymous functions without a name. These are useful for short, one-time operations, especially when working with concurrency or callbacks. Finally, Go provides the defer keyword. It delays execution of a statement until the function finishes. This is perfect for cleanup tasks like closing files or releasing resources. And now, you understand how functions work in Go, one of the most powerful tools in the language. As your programs grow, managing individual variables quickly becomes messy. Imagine storing dozens or even hundreds of values, one by one. To solve this, Go provides collections, starting with arrays. As your programs grow, managing individual variables quickly becomes messy. Imagine storing dozens or even hundreds of values, one by one. To solve this, Go provides collections, starting with arrays. Each element in the array has an index, starting from 0. You can access or modify values using this index, making arrays easy to work with. You can also initialize arrays with values directly. This makes your code shorter and more readable when you already know the data. But arrays have a limitation. Their size is fixed. In real applications, you often need something more flexible. That's where slices come in. A slice is a dynamic version of an array. It doesn't have a fixed size, which makes it much more flexible for real-world use. You can add elements to a slice using the append function. Each time you append, the slice grows automatically to fit the new data. Slices have two important properties: length and capacity. Length is how many elements are currently in the slice, while capacity is how much space is available before it needs to grow. You can create slices using the make function, where you define length and capacity. You can also create subslices using slicing operations, which lets you work with parts of existing data. To work with slices, you often loop through them using range. This gives you both the index and the value for each element. For better performance, it's often useful to pre-allocate capacity using make. This reduces memory reallocations and makes your programs more efficient. And now you understand arrays and slices, one of the most important concepts in Go. As programs grow, you often work with related data, like a user's name, age, and email. But storing them as separate variables quickly becomes messy and hard to manage. What we really want is a way to group related data together, so it behaves like a single unit instead of separate pieces. In Go, this is done using structs. A struct is a custom type that groups multiple fields together into one structure. Each field has its own name and type. Once defined, you can create a struct using a literal. This allows you to assign values directly when creating the object. If you don't provide values, Go automatically assigns 0 values. Strings become empty, numbers become 0, ensuring your struct is always initialized. You can also create structs using the new keyword. This returns a pointer to the struct, which is useful when you want to modify the original data. To access or update values inside a struct, you use dot notation. This makes working with structured data simple and intuitive. Instead of inheritance, Go uses composition. You can embed one struct inside another, creating more complex structures while keeping things simple and flexible. Sometimes you only need a struct temporarily. In those cases, you can use an anonymous struct, defined and used in a single place. So far, structs help us organize data, but real programs also need behavior, actions that operate on that data. In Go, you can attach functions to structs. These are called methods. With a value receiver, the method works on a copy of the struct. This means any changes made inside the method won't affect the original data. Sometimes that's useful, but sometimes you need something more. To modify the original struct, you use a pointer receiver. This allows the method to work directly on the real data, making updates permanent. The difference between a function and a method is simple. A function is independent, while a method is tied to a specific type. This helps organize logic around your data. Structs organize your data, and methods define how that data behaves. Together, they form the foundation of building real-world applications in Go. And this is where your code starts to become truly powerful. In programming, different types can often share similar behavior. For example, a dog, a robot, and a human can all make a sound. But if we handle each one separately, our code quickly becomes repetitive and hard to scale. Interfaces solve this problem. An interface defines a set of method signatures, like a contract that types can follow. Any type that implements these methods can be treated the same way. In Go, implementation is implicit. This means you don't need to declare that a type implements an interface. If the methods match, it automatically satisfies the interface. This keeps code simple and flexible. Interfaces become especially powerful when used as function parameters. Instead of writing multiple functions for different types, you can write one function that works with any type that satisfies the interface. At this point, interfaces allow us to write more general and reusable code. But sometimes, we don't even know what type we're dealing with. The empty interface can hold any value. Because it doesn't require any methods, every type satisfies it. This makes it extremely flexible, but also requires careful handling. When working with unknown types, we need a way to figure out what we're actually dealing with before using the data. Type assertions let you extract the underlying value from an interface. You specify the expected type, and if it matches, you can safely use it. Otherwise, it can fail, so it must be handled carefully. For handling multiple possible types, Go provides type switches. This allows you to check different types in a clean and structured way, without writing multiple assertions. Interfaces are one of Go's most powerful features. They allow different types to work together through shared behavior, making your code flexible, scalable, and easy to extend. And this is what makes Go so elegant. In real-world programs, things don't always go as planned. Files might not exist. Network requests can fail. And if we don't handle these situations properly, our program can break. Unlike some languages, Go doesn't rely on exceptions. Instead, it uses a simple and explicit approach. Errors are just values that are returned from functions. In Go, errors are built on a simple interface. Any type that implements an error method can be treated as an error. Functions in Go often return 2 values, the result and an error. This makes it clear that something might go wrong and forces you to handle it explicitly. After calling a function, you always check if an error occurred. If ER is not a nil, something went wrong, and you need to handle it before continuing. This pattern might seem repetitive, but it makes your code predictable and safe. You always know where errors can happen, and you deal with them immediately. You can create your own errors using the errors package. This allows you to return meaningful messages when something fails. For more detailed messages, you can use formatted errors. This lets you include dynamic data, making debugging much easier. For more advanced cases, you can define custom error types. By implementing the error method, you can create structured and meaningful error handling. At this point, error handling becomes part of your program's flow. Not an afterthought, but a core design decision. One of the most important rules in Go is to never ignore errors. Skipping error checks might seem convenient, but it can lead to serious problems later. One of the most important rules in Go is to never ignore errors. Skipping error checks might seem convenient, but it can lead to serious problems later. By default, programs run one task at a time, each operation waiting for the previous one to finish. But in real-world applications, this quickly becomes inefficient, especially when tasks could run independently. What we really want is to run multiple tasks at the same time. This concept is called concurrency, and in Go, it's built directly into the language. In Golang, concurrency starts with Goroutines. By simply adding the Go keyword before a function call, you can run that function asynchronously alongside others. Concurrency means managing multiple tasks at once, while parallelism means executing them at the exact same time. Go focuses on concurrency, but can also leverage parallelism when available. Once you have multiple Goroutines running, they need a way to communicate safely, and this is where channels come in. A channel is a way for Goroutines to send and receive data. You create one using the make function, defining the type of data it will carry. Data flows through channels using arrows. You send data into a channel and receive it on the other side. This creates a safe communication path between Goroutines. By default, channels are unbuffered. This means sending and receiving must happen at the same time. If one side isn't ready, the other side waits. This blocking behavior is powerful because it naturally synchronizes your Goroutines without needing complex locking mechanisms. But if no Goroutine is ready to receive, the program can get stuck. This situation is called a deadlock, and it will crash your program. To avoid constant blocking, Go provides buffered channels. These allow you to store a limited number of values, so sending doesn't immediately require a receiver. When you're done sending data, you can close the channel. This signals that no more values will be sent. You can iterate over a channel using range, receiving values one by one, until the channel is closed. When working with multiple channels, the select statement lets you wait on several operations at once. It executes whichever channel is ready first. You can also add a default case, which runs if no channels are ready. This prevents blocking and keeps your program responsive. Goroutines allow you to run tasks concurrently, and channels allow those tasks to communicate safely. Together, they form the foundation of Go's concurrency model, making it simple, powerful, and efficient.